Morning. The topic I am going to talk about is low temperature storage systems, Linde and Claude system for liquefaction of air. Conditions of liquefaction of gases. Many industrial processes require large quantities of liquid air, liquid ammonia, liquid carbon dioxide, etc. The production of liquids from various gases is therefore an important commercial operation. There are different methods of liquefaction of gases, such as based on concept of critical temperature followed by the compression, based on Joule-Thomson effect, adiabatic demagnetization. In the cases of gases like ammonia, chloride, sulfur, SO2 and carbon dioxide, those critical temperature values are near and below the ordinary temperatures. They can be liquefied easily by increasing the pressure alone at their respective Tc values. Gases like hydrogen, oxygen and nitrogen and helium have very low critical temperature values and hence Joule-Thomson effect may be applied to bring in effective cooling. Helium is cooled by Joule-Thomson effect to a lower temperature and further cooling for its liquefaction is carried out by the method of adiabatic demagnetization. Linde's method. In this method, as you can see on the right side corner, this is the apparatus used for Linde's. This is the Linde's apparatus used for liquefaction of gas. In this method, it makes use of Joule-Thomson effect, and it is simply used to liquefy air or any other gas. Pure air or any other gas is first compressed to about 200 atmospheres and is allowed to enter the inner tube of the concentric pipes as shown. The valve V of jet J is then opened and the gas is allowed to expand suddenly into the wide chamber C. The gas gets cooled due to expansion and its pressure is reduced to about 50 atm. It is not allowed to pass through the outer tube O. At this stage, the incoming gas is initially cooled by the outgoing gas. Further, cooling of the incoming gas occurs during expansion in the chamber C. The cooled gas is again compressed and circulated in. By repeating the process of cooling and compression followed by expansion, the gas is liquefied and finally the liquid air drops out from the jet into the bottom of the chamber C. Now we are going to see about the merits and demerits of Linde's process. The Hampson-Linde cycle introduced regenerative cooling, a positive feedback cooling system. The heat exchanger arrangement permits an absolute temperature difference, that is 0.27 degrees Celsius per atmospheric temperature joules and temperature of cooling for air to go beyond a single stage of cooling, and it can reach the low temperatures required to liquefy fixed gases. The Linde cycle uses isenthalpic expansion, which has two drawbacks. Firstly, the expansion work is lost, and secondly, cooling cannot be achieved if the fluid is in thermodynamic state is such that Joule-Thomson expansion leads to a temperature lowering. Claude's process. In this method, the compressed air is allowed to do mechanical work of expansion. This work is done at the expense of kinetic energy of the gas and hence a fall of temperature is noted. The principle is combined with Joule-Thomson effect and utilized in Claude's process of liquefaction of air. Air is compressed to about 200 atmosphere and is passed through the pipe ABC. At C, a part of air is going to the spiral towards the jet nozzle and a part of air is let into the cylinder D provided with an airtight piston. Here, the air moves the piston outwards and it expands the volume, as a result of which considerable cooling is produced. The cooling air passes up the liquefying chamber during the process and it cools the portion of the incoming compressed air. This pre-cooled incoming compressed air then experiences Joule-Thomson expansion when passed through jet nozzle J and gets cooled further. The above process takes place repeatedly till the air is liquefied. Merits and demerits of Claude's process. The advantages of this cycle is that compression ratio can be significantly lower than in case of Linde cycle. One difficulty is that the expansion machine cannot operate with good efficiency if the fluid remains in the vapor zone or keeps a high quality. Adiabatic demagnetization. Generally, the method used to reach the very low temperature of about 10 to 4 Kelvin is adiabatic demagnetization. In this method, the paramagnetic samples such as gadolinium sulfate is placed surrounding the gas sample and cooled to about 1 Kelvin along with the gas in any one of the cooling methods. The paramagnetic sample used in this method is suddenly magnetized by the application of strong magnetic field. This magnetization occurs while the sample surrounds the cooled gas and has the thermal contact with the walls of the container. When the magnetic field is suddenly removed, demagnetization occurs, which brings in a disordered state of the molecular magnets. To reach this state, thermal energy is taken away from the cooled air such that its temperature gets further lowered. By this technique, as low as 0 Kelvin is achieved. There are few drawbacks in adiabatic demagnetisation, such as if the sample material is an electronic paramagnet, the lowest temperatures possible it can be achieved using these methods. Due to weaker interaction between dipoles, temperature can be achieved at low temperatures if the sample contains a nuclear paramagnet. The applications of adiabatic demagnetisation. It is a cooling process and it is found in magnetocaloric material. These materials heat up in magnetic fields and then cool down when they are moved from the magnetic field. It is used in magnetic refrigeration process to attain low temperatures such as cryogenic labs. Thank you.